Hello friends, we studied frequency scaling and impedance scaling technique is used for transformation of low pass prototype filter into a desired filter. In this video, we are going to transform low pass prototype to low pass and high pass filter. First, we'll see low pass prototype to low pass filter. First, I draw the frequency response of low pass prototype. Frequency response is PLR versus omega. This is a frequency response of low pass prototype. So upper edge represented as a 1 and lower edge represented as a -1. This band is a pass band where insertion loss is less. Now our aim is to convert low pass prototype into a low pass filter. So accordingly, I draw the real or a desired low pass filter response. This is a low pass filter response. It is PLR dash right here, PLR dash versus omega. It's a low pass filter. It has the same response, but upper edge represented as a omega c and minus edge represented as a, or lower edge is represented as a minus omega c. So for conversion from low pass prototype to real low pass filter is performed by replacing omega by omega upon omega c. Therefore, the component becomes a series impedance is represented in terms of a frequency scaling becomes jxk. It is equal to say omega lk, replace omega by omega c, modify this equation as j omega lk by omega c. Right here j omega lk dash, where lk dash equal to lk by omega c. Same as we will calculate shunt susceptors, that is jbk, it is equal to j omega ck. Omega is replaced by omega c. Right here j omega ck by omega c equal to j omega ck dash, where ck dash equal to ck by omega c. So it is a frequency scaling. Now we apply impedance scaling on this part, then we'll get a result. Right now, applying impedance scaling, the component becomes lk dash equal to lk by omega c. For Lk, we multiply R0. This is a impedance scaling for Ck dash, Ck divided by omega C. So it is a divided by R0, means Ck divided by R0 multiplied by omega C. So means for a low pass prototype, so this is a low pass prototype, and this represents real or a desired low pass. Inductor Lk in a low pass prototype is transformed in a desired desired low pass filter as Lk dash equal to R0 Lk by omega C. Then capacitance Ck is represented as Ck dash is the transformation equal to Ck divided by R0 omega C. Okay. So this is called as a transformation of low pass prototype into the desired low pass by using impedance scaling and a frequency scaling technique. Okay. Now we'll see a next part, low pass prototype to high pass filter. I draw a response. So this is a response of the low pass prototype. PLR, first one, minus one. We have studied in the previous part. So PLR dash versus omega. So if you draw the response, this is a response. So this response is a PLR dash of low pass filter is omega C and minus omega C. Now we draw a response of high pass filter is omega. So here PLR double dash this is a high pass filter response. Omega C is 0 minus omega C. Here in a low pass filter, this band acts as a pass band. Where is the insertion loss is less. So what happens in a high pass filter? This band acts as a pass band. It is a insertion loss is less. If we see carefully, both are inverse frequency response. Therefore, for conversion of low pass prototype to high pass filter, we do one thing: replace omega by, we reverse this, omega C by omega, right? It is a minus to get positive inductance and capacitance value. For that purposes, we put here minus. Therefore, write shunt impedance J XK, it is equal to J omega LK. Replace omega by minus omega c by omega, so write J minus omega c by omega Lk. Right here becomes minus J omega c Lk by omega. So right here 1 upon minus J becomes divided by J omega Ck dash. So where Ck dash becomes equal to 1 upon omega c Lk. If you see carefully in this figure, low prototype, first prototype has an inductance which becomes a capacitance in a high pass filter. Get it? So we know that in the low pass filter and high pass filter, the components are interchanged to each other. In the low pass filter, inductor is in series, but in a high pass filter, capacitor is in series. Same as if capacitor in a low pass filter is in shunt, then inductor is in shunt in a high pass filter. Simple to represent here. Inductor is in series, that component is interchanged by a capacitors in a high pass filter. Same part, we write here shunt susceptance J dk equal to J omega ck. Same part, omega is replaced by minus omega c by omega. J minus omega c by omega ck equal to minus J omega c ck by omega. So right here 1 upon J omega Lk dash, where Lk dash equal to 1 upon omega c ck. Friends, now see carefully. Here, in a low pass prototype, in a shunt branch, there is a capacitance, but it is interchanged in a high pass filter by a inductor. There is a interchange of components. Now, applying impedance scaling. Impedance scaling. So right here, Lk dash equal to 1 upon omega c multiplied by ck. Already we know that for Lk dash we multiplied by a R0. Then for ck dash it is 1 upon omega c, then Lk. For ck it is divided by R0. Therefore ck dash becomes 1 upon R0 omega c Lk. This is components we will get by using impedance as well as a frequency scaling. So I show the components of low pass prototype to high pass filter transformation. The series component in low pass prototype is a inductance, is given as Lk. It is transformed into the high pass filter by a ck dash. How to write Ck dash? Ck dash, it is equal to 1 upon R0 omega C Lk. See carefully here. This inductance becomes a capacitance in a high pass filter. Same as capacitance Ck in a low pass prototype becomes a inductor in a high pass filter represented as Lk dash equal to R0 divided by omega C Ck. How do we transform these? We transform these by using frequency scaling and impedance scaling technique. Thus, by using these techniques, we can easily transform low-pass prototype filter design into a desired filter. Thank you.